Good morning. Welcome to this webinar on how to create a safe and effective electrical maintenance program. This webinar is brought to you by IRIS, global leaders in the manufacture and design of electrical maintenance safety devices. Now, during this webinar, we intend to cover certain points, i.e. the business case of the electrical maintenance program, arc flash accident and injury statistics, the challenges that you will face setting up an electrical maintenance program, critical asset surveillance technologies or CAST, maintenance-induced failures and reduction strategies associated with them, asset maintenance strategies, equipment failure modes, the benefits of a critical asset surveillance technologies maintenance program, and the electrical maintenance safety devices benefit analysis that are associated with using CAST. Now, our electrical systems are the lifeblood of our company, absolutely critical to everything. So, managing these systems and the maintenance plans are super important. Looking at the business case for electrical maintenance, you really start to break down and ask yourself the following questions. What is the dependence on electrical energy and control systems within your company? What are the consequences of an unplanned mishap or in your electrical system? How long would it take you to recover from an unplanned outage? And how are you going to go around improving your electrical system's reliability? All of these will have a huge impact on your company. Losing power, everything stops. That means you're going to start losing money across the board. So you need to break into these systems and work out what's going on. When you look at your profits within your company, the basic principle we say in a company is the avoidance of loss. We can maximize the profits, but if we're hemorrhaging money through losses, it really doesn't matter how profitable our company is. So avoidance of loss has a significant impact on the bottom line from day one. You're going to start to hear the term return on safety. CFOs are now including ROS as a line item on the balance sheets. What we're seeing is that even OSHA states like for every $1 you invest in your safety, you can expect a $4 to $6 return. So huge paybacks on that. If you look at man-hour reductions for critical asset inspections, we see utilising things like electrical maintenance safety devices. We can see reductions of up to 95% in man-hours and massive impacts on the mean time between failure on equipment. And we're going to go into that in a lot more detail later on in this presentation. Another thing that we see, fires, non-residential fires where electrical malfunctions are listed as a cause, were over nearly $4.7 billion in the United States in a 10-year period. Then we've also seen a recent report, a blackout tracker report from Eaton, where they estimate that power disruptions cost the US economy $150 billion in 2015. The report also states that according to Dun & Bradstreet, that 59% of Fortune 500 companies experience a minimum of 1.6 hours of downtime per week. Now, when you start breaking that down, if you assume there are 10,000 employees and the average salary is $56 per hour, including benefits, then the downtime for a Fortune 500 could cost a whopping $896,000 per week, which is more than $46 million annually. So from a business standpoint, there are huge financial returns by getting this right. Now, if we look at arc flash incident and injury statistics, there are 1 to 2 arc flash related fatalities that occur in North America every day. Electrocution is the 5th leading cause of workplace fatalities in the United States. 60% of workplace fatalities are caused by burn injuries. Electrical shock is the 2nd leading cause for lost time on the job, second only to burn. So when you look at the electrical injuries that you see, it's either shock or burn, and these are 1 and 2 on the scale of criticality. 97% of electricians have been shocked or injured on the job, and every 30 minutes during the workday a worker suffers an electrically induced injury that requires time off work for recovery. And 80% of electrical related accidents and fatalities involving qualified workers are caused by arc flash or arc blast. 2,000 workers are treated in specialised burn and trauma centres each year as a result of arc flash injuries. Now, if you are involved in an arc flash and you get a minor burn, i.e. a 2nd degree burn, and doesn't require extensive treatment, i.e. you went to an emergency room, that is not included in these figures. This is only the people that have ended up in a burn centre actually get included on these figures. So these numbers are much higher. Medical costs for severe electrical burns can exceed $4 million per person. Now, the cost of their treatment and rehabilitation is huge. Now, another significant statistic is that field tests and surveys have shown that 22% of breakers operate at less than 100% efficiency, i.e. there's a slow trip, and more than 10% have been shown not to open at all. So this is, we rely on our breakers, and this is why breaker maintenance is so important, because if the breakers don't operate, then our calculated arc flash exposure is much higher than what we've calculated it to be. Now, more accidents occur in 480 volt equipment than on higher voltage, and I hear people tell me, say, well, it's only low voltage, it doesn't matter. But really, the higher voltage has much lower available fault currents and much faster clearing times, so the actual incident energies are not as high as that we see in 480 volt equipment sometimes. So again, be very careful if we are saying, oh, it's only low voltage, we're okay. You're not, you're never okay. So the challenges that we have to face, from a day-to-day, if I want to implement an electrical maintenance program, there's a few things I need to do. So I need to create a solution for collecting on-demand, real-time condition status data of mission-critical electrical distribution systems and components. I'm trying to mitigate the thousands of electrical worker injuries each year, some fatal, and billions in lost revenue from unplanned outages and equipment failures. We're trying to implement comprehensive, safe and intelligent protocols for performing essential energised surveillance and inspection procedures on electrical distribution systems. And we're trying to remove the inherent dangers of condition-based maintenance procedures and still allow for efficient routine inspections on demand. Again, I need to look into my equipment routinely. So when we look at critical asset surveillance technologies, or what we call CAST, basically this refers to monitoring technology or equipment that's in use every day on our electrical distribution assets. These surveillance methods determine the condition of the equipment that we're looking at, and the sort of tools we're using is infrared thermography, airborne ultrasound, motor current analysis, partial discharge testing or corona cameras, power quality monitoring, and the vision inspections. These are all part of what we have to do on a daily basis, on a routine basis on our electrical equipment. A daily basis would be great, but there are a lot of hurdles involved with doing that. Now, the main issue surrounding the implementation of a CAST program is, the inspection and surveillance equipment normally yield their most valuable results when inspecting under full load conditions. In fact, NFPA 70B recommends a minimum of 40% load when we're doing an infrared inspection. Now, CAST equipment input normally requires a direct access or direct line of sight for energised components in the electrical systems, which requires either panels to be open, or we need to shut down. So we don't want to shut down because we want to underload, and we don't want to open the panels because we recognise that's a very, very dangerous condition. So utilising EMSDs or electrical maintenance safety devices enables me to use the critical asset surveillance equipment such as infrared and ultrasound, etc., and visual through either windows or ports, because that keeps the panel in an enclosed and guarded condition, which enables me to use the CAST equipment, get the data I need, but never open the panel and never put myself in harm's way. So at IRIS we have what we call our protection model. Now the IRIS PPE model outlines how electrical maintenance safety devices protect people, profits and equipment. The value of EMSDs really is their ability to be implemented into any maintenance regime and deliver immediate, measurable returns and results for documentable CAST program and safety upgrades, personal and resource allocation efficiencies, and measurable and sustainable financial returns. If it ain't broke, don't fix it is a term I've heard many, many times. And when applied to personal safety, maintenance procedures, and the physical condition of mission critical assets, it really takes on an entirely different meaning. So what we're trying to do now is we're trying to fix the way or change the way we maintain our equipment by making sure we do routine monitoring but safely. So looking at maintenance-induced failures, the use of electrical maintenance safety devices to facilitate a cast-type inspection regime reduces the requirement of hands-on calendar-based maintenance. And by reducing these hands-on tasks, we also reduce the number of maintenance-induced failures that affect your organisation. Human error is inevitable, and using electrical maintenance safety devices allows us to design our systems and processes around this inevitability. Looking at reducing maintenance-induced failures is a critical area where we utilise EMSDs, because we ensure that we don't over-maintain our equipment, and we improve the quality of how the maintenance activities are actually completed, which includes error proofing where required. So an EMSD is like a poka-yoke device, or it's a Japanese term, means mistake proofing. So a poka-yoke is a mechanism of lean manufacturing process that helps the equipment operator avoid mistakes. So again, utilising an EMSD, we know the results we're looking for, we know the equipment we're utilising, and it really makes the whole process much easier to follow. So the EMSD really then becomes what we call a data collection point for the critical asset surveillance equipment, where we simplify inspection processes and identify all the required parameters prior to the inspection. So therefore the inspector knows, using an infrared camera for instance, what the critical temperatures are. If they're using ultrasound, they know what the dB level should be, etc., etc. KISS is Keep It Simple Stupid. Inspection programs utilising CAST and EMSDs ensure that the task of data collection and equipment monitoring is simple and repeatable. Now, what KISS isn't meant to imply is stupidity. On the contrary, it's usually associated with intelligent systems that may be misconstrued as stupid because of their simplistic design. Albert Einstein said it very well, where he said everything should be made as simple as possible, but not simpler. This means that one should simplify the design of a product, and success is achieved when the design is at its maximum simplicity. Another area where you want to look at is asset maintenance and design strategies. Strategies such as those detailed in ISO 55000, which is the asset management standard, which are focused on life cycle cost and risk-based performance. ISO 55000, for instance, details processes which should be considered from a perspective of the site's original concepts, the equipment you're going to need, its specifications, its use and maintenance throughout its life cycle, all the way through to final disposal. It's what we call sort of a lust to dust asset management model. Involving your OEM as part of your asset management design strategy is imperative. Engaging an OEM as a partner directly impacts the following. As much as 60% of failures and safety issues can be prevented by making changes in design. 80% or more of facilities' life cycle costs is fixed during the plan, design and build phases, and 30 to 40% of equipment breakdowns are related to poor equipment design or conditions. So it's imperative that you get involved with your OEM as part of your design strategy. We need to apply the fundamentals of asset design to the conceptual and preliminary design phases of capital projects to help identify the best OEM partners for their projects. OEMs will be able to optimize the design maintainability, reliability and performance of the assets they build, but to do this they must fully understand the requirements placed upon the asset, and the following things really need to be considered. A request for information will identify the best positioned OEMs to leverage reliability and automation as a partner and stakeholder. Engineering specifications integrate detailed maintenance and reliability standards and specifications into your designs from the beginning. An important area of consideration before entering your electrical maintenance plan is really to understand how things fail and what critical asset surveillance technologies or CAST techniques are available to you to find those failures. Now, the sort of tools that we're currently using, and we're going to go through a few, we're going to look at ultrasound testing, motor current analysis, infrared thermography, and the electrical maintenance safety devices that these equipment will utilize to enable them to monitor the fully energized equipment, but through an enclosed and guarded condition. Back in the 60s, two guys called Nolan and Heap did a study, and it was basically they were trying to find out how things failed. The reliability centre maintenance curves really came from out of that study that they did way back in the 60s, but they're still relevant today. So these curves are the age-related behaviour curves, which graph the conditional probability of failure against age. The patterns of failure illustrate failure probability against time and can be split into two broad categories. Age-related failures are wearing out, and random failures where there's no particular wear-out pattern. Now, prior to this study, really most people were under the consideration that things failed because they wore out, but this study showed that not to be the case. What we can see from these curves is basically age-related failures are only responsible for 11% of the failures that we see in an equipment's lifetime. And in particular, the big ones that really were, of a big surprise were infant mortality, which is, 68% of failures will be seen in the first couple of years of a piece of equipment's life. And random failures with 14%, initial braking period 7%, but the non-age related failures were responsible for 89% of the failures that we were seeing. So once we started to look at these, how things broke, and looking at how things operate, we then started to come up with curves and ways of predicting or working out when things are going to fail. Now, looking at electrical PF curve, the PF curves are something that we utilise in electrical maintenance. The P stands for the point of potential failure. That's an identifiable physical condition which indicates a functional failure is imminent, and the F is a functional failure, which is the inability of an item or equipment contained in it to meet a specific performance or standard. So relate this to you use your car every day, you get in the morning and you're driving it doesn't feel right. Nothing right, maybe a check warning lights come up, but that's a point of potential failure. So the car's still running, but it's not running well. And then all of a sudden the car stops. Well, the car stopping is a functional failure of that device. So if the car's not driving, it's failed. So that's where you can allocate or start to look at the PF curve and trying to identify these points of potential failure before we get stopped on the side of the road. So when you look at this electrical inspection PF curve, obviously if you look at the curve on the bottom, the longer we leave it, the higher the cost of repair till it gets to an extent it's just not worth doing. P is the point of potential failure, and we're looking for early signals using CBM, condition-based maintenance, or CAST or surveillance technologies to try and identify these problems before it gets to hot to the touch and audible noise, etc., and then it just goes bang. So we're trying to avoid that. The earlier we find it, the lower the cost of repair and the better it is for the asset. So let's look at an electrical system now. Okay, we've got a point of potential failure. We come up to the early signal one where we're going to use ultrasound infrared motor current analysis. So looking at the curves, obviously the motor current analysis, slight increase maybe at this stage. No abnormal thermal patterns probably detected at this stage, but we will pick up something called corona, which sounds like this. And what the corona is basically the start of the connection starting to fail. The air gap starts to break down. Now we're using the electrical maintenance safety devices, IR windows, ultrasound ports, and voltage or tap-off ports for to measure the motor current analysis data. And all of this is being done closed, and quick and efficient. We've already predetermined, as we said earlier, like the poker yoga device. We've error-proofed. We've shown what we need to do. So at this stage, we may not decide to do anything. We'll just make a note. We leave it a little bit longer, and we go back. Maybe we've increased our inspection frequency because we picked up corona. Here we now, as it gets worse, the motor current analysis, the resistance, voltage testing, etc. is going to start to show signs of failure. Thermal patterns are going to start to develop, showing signs of failure, and we may now move into hearing something called tracking. And tracking sounds like this. Now, all of the time, we're utilising the EMSDs, we're maintaining an enclosed and guarded condition, and we're getting this stuff back, we're getting the data back quickly and safely. Now, if we decide to ignore these signals, the faults will start to get worse, and they'll advance to the stage 3 that you can see on the plot at the moment. Now what stage 3 will show us, then you're going to see motor current analysis, voltage and current measurements. All these readings are going to start to increase significantly, way outside of acceptable alarm levels. We will see thermal patterns expanding rapidly, again outside of the acceptable alarm levels, and you're going to then come, well hopefully you won't, but you may come across the third phenomena that we can find with ultrasound, which is arcing. And arcing sounds like this. The arcing has a very definitive sound, very definite. You can find if you hear that, you've got real problems. Now don't forget, all of this again, you're using the EMSDs, infrared windows, ultrasound ports, voltage and current tap-offs. So once we've gone through these early signals using the condition monitoring equipment, if we allow the equipment to run to a failure, you'll start to see physical conditions change. You know, you'll be hearing things as well. Things will be hot to touch. The cost of repair now would have gone up exponentially. In some cases, it may be so high that it really isn't financially viable to repair the equipment. So, you know, looking at the PF curve, you know, doing something when you find these early conditions and having an action plan in place that if you reach a critical temperature measurement, or you hear a dB level, or you see a current or voltage measurement that exceeds an agreed alarm level, you can do the repairs before you get to these stages where really the equipment's been enabled to run in these failure modes for too long. So looking at condition-based maintenance, okay, if you look at this curve here, this is an installation to point potential failure to a functional failure curve. So look at it more of a life cycle curve. Now with condition monitoring, you know, condition-based maintenance or critical asset surveillance technologies, we really can do something quite special on these curves. Yeah, what we can do is by monitoring routinely using critical asset surveillance technologies, we can see the point of potential failure, we can repair before it gets too bad, before we get to a functional failure, and expand the life cycle or the lifetime of the equipment, which really then gives us, you know, real payback. You know, if we can get more out of our equipment, we can run it for longer, then our investment is returned significantly. Now looking at this EMSD benefit analysis, let's make safety device benefit analysis, I'm going to look at using infrared windows and ultrasound ports. Now this is basically, when we look at an electrical survey, typical 3-man team, you've got 2 electricians for panel removal and refit. One electrician shouldn't manhandle a panel on an energized. Really, you don't want to be opening an energized compartment anyway. But if you are, it's not done by one person. You need a couple of pairs of hands on that, because the last thing you want to do is drop a panel into an energized piece of equipment, because that's when significant accidents happen. Also here we have a reliability center maintenance engineer who's contracted to do this task. So if you look at PPEs, first and foremost put the PPE on, 30 minutes to dress out in PPE. That's for 2 electricians and 1 RCME. That's 1.5 man hours, yeah, which has to be paid for. The panel removal and refit, 30 minutes for 2 electricians. Now obviously if it's hinged or has different compartments, you know, that can be significantly faster, but on some older panels, really heavy panels, it can be slower, because don't forget the guys that are doing this are fully suited in PPE, which slows down the work rate significantly. The actual infrared and ultrasound inspection takes minutes, yeah. So here we've put 10 minutes for one guy. What the RCM engineer has been contracted to do this. Panel refit, another 30 minutes, 2 guys. Then you all move on to the next panel. So we're looking at about 1 hour for 3 people, which is 3 man hours, and that excludes the PPE suit up time, etc., etc. Now, if we look at a cost analysis of a job that was conducted at a paper mill, this paper mill had 150 pieces of primary switchgear that were inspected annually. And the reason they were inspected annually, because obviously we've gone through, energised inspections are intrusive and extraordinarily dangerous. So a lot of companies don't do them, and those that do them only do them on an annual basis, and 9 times out of 10 it's for insurance requirements. The infrared and ultrasound inspections were completed energised and in full compliance with NFPA 70E and 70B. They were completed by 2 plant electricians, and these plant electricians were required for panel removal, and the one contract RCM engineering company that did the infrared and ultrasound inspections. And the inspections currently take approximately 150 hours to complete. So looking at the analysis of the critical asset surveillance technologies inspections, we're going to look at the PPE Suit Ups. Now this estimation at the time was based on 2 Suit Ups per day, which was for 21 days, 3 weeks, a total of 42 dress outs. Now this was way off. This inspection was completed in 102 degrees in the paper mill. You can't sit in PPE all day. So there was about 6 suit ups, but again, this was done for budget costings. The RCM, so looking at those budget costings, the RCM engineer, half an hour suit up time, 21 man hours to put his PPE on. Electrician PPE suit up time, 42 hours. So you've got 63 hours of suit up time for PPE. Now if you actually look at the actual task itself, 150 panels, half an hour per panel to remove them. It's 150 man hours because there's 2 electricians. The RCM inspection only took about 15 hours. The RCM engineer, who's the most expensive guy on the job, is sitting there for 150 hours watching the electricians remove and replace panels. The electricians are sitting there for 30 hours watching the RCM engineer do his infrared and ultrasound scans. So the manpower for this whole job was 495 hours, plus the PPE suit up time is 558 man hours. So this is the crux of this. Only 15 hours are what we would class of productive labour. Yeah? The other 543 hours is 97% of the hours that you're paying for on this job are dangerous, high risk, unproductive labour. So again, really, from a process standpoint, live inspections are very, very time consuming, dangerous and high risk. Now, if we look at the inspection with electrical maintenance safety devices completed, obviously because there's no panel removal, there's no suit up time. So all of that PPE time goes away. You do the inspection in your everyday PPE because you leave the panel in an enclosed and guarded condition. That way you haven't got to increase your PPE. Obviously no cover removal or replacement. The actual RCM inspection, the paper mill then had their own camera to do this job once they put the EMSDs in. We gave the inspector 30 hours and that included writing the report. The physical job actually took about 7 hours, and then there was the post-processing and everything else of the report. So the man hours for this job then went to 30 hours. Now that was 30 hours 100% safe, low risk, productive labour. Okay, so now if you expand from this, we'll look at the man hour savings. The critical asset surveillance technology inspections went from 558 man hours using a 3-man inspection team to 30 man hours using one guy. This equates to real world savings of 97% on the man hours needed to complete this task when the electrical maintenance safety devices were completed. Now the other thing that comes from this is that more inspections are done. Because we've removed these hurdles to energise inspections by making them much safer, much more efficient, then we find that the companies that adopt this technology do a lot more inspections, and by doing a lot more inspections, obviously we're going to find things before they get worse. Looking back on the options that we went through on the PF curve earlier. Now, Emerson do, from a critical power standpoint, I mean, they're really about as good as it gets. And there was a recent study on the effect of regular skill preventive maintenance and remote monitoring of critical power systems reliability on something called mean time between failure, MTBF. Now, those that do a lot of reliability work, MTBF, or mean time between failure, is a significant metric that we use when we're looking at the efficiencies and trying to improve the way we do our maintenance. Now, this study showed the following results. Looking at this curve here, this is a curve that compares the maintenance, scheduled maintenance on equipment that is using online monitoring. And we can see that basically, if you just do one inspection a year and you put online monitoring systems in, you can increase MTBF by, up to 10 times. Do 4 inspections a year, we can increase the MTBF by 51 times, and even by doing the inspection 6 times a year, we can increase it by 82 times. These are extremely significant figures because MTBF is a very significant metric that we use when we're trying to qualify the type of maintenance we're doing and its effect on the overall asset reliability. So to summarise what we've gone through, the use of electrical maintenance safety devices in these surveillance strategies really does provide the following benefits. We remove the high-risk behaviours associated with open panel energised inspections of electrical assets by maintaining what NFPA classes as an enclosed and guarded condition at all times during the inspection. That means that the workforce or the inspectors are never ever exposed to energised components, therefore removing the elements of arc flash or electrocution by contact. We conduct fully loaded inspections in line with the requirements of NFPA 70B. We don't need load banks or anything. We're looking at the equipment at peak load times and actual operating conditions, which for an engineer is a far more valuable inspection to make. We access inaccessible equipment. One thing I didn't mention back when I was going through the paper mill scenario was that actually 17% of their primary switchgear had arc flash hazard in excess of 40 cal. So those were never actually looked at. So really, that doesn't make sense. You need to 100% of your electrical equipment because it only takes one piece to knock you out. So again, we can access inaccessible equipment because we don't open the panels. We don't have elevated risk levels, therefore things can get done more easily. Inspections are much faster. Okay, we're not removing panels, we're not putting them on PPE. We're basically going around in our everyday PPE and we're making as many inspections as we need to. The less manpower required, obviously. Only one person is required to operate the equipment and open the EMSD, so we're not using up that valuable manpower for doing very high risk laborious work. Lower personal protection equipment levels, obviously, because we're not in front of energised equipment. We have increased inspection frequencies, which is a huge payback. We train our people, we buy this equipment. The more we can get out of that training and the equipment, the better it is for us as asset managers. So we're going to do a lot more inspections. And we have an increase of ROI on the cast equipment and training that we've invested in. As the great Edward Deming once said, you can't manage what you don't measure. And that really is nothing as true in maintenance. The electrical maintenance safety devices that you're going to use in your critical assets surveillance technologies really will give you the ability to inspect this equipment much more routinely, much safer. And with the data we're going to get back, looking at the PF curves, we can really make some good sound engineering decisions on when we need to repair our equipment and what needs to be done on it. So again, the measurement is key. It really is. Thank you for attending this webinar. We hope you found it useful. There's a lot more information available to you on electrical maintenance safety devices and critical asset surveillance technologies on our website, www.iris.com. But now we're open for questions on anything you might want to ask regarding the EMSDs or CAST or other issues that we covered in the presentation.